this video, I'm going to demonstrate how to graph a hyperbola in the Connect and ALEKS systems. So we have a hyperbolic equation, y squared minus x minus 3 quantity squared divided by 20 is equal to 1. And our directions are to identify the center, identify the vertices, identify the foci, write equations for the asymptotes, and then graph the hyperbola. And we've been reminded that we need to give exact answers. Remember, this homework system does not allow approximation. And we're to express numbers in simplest form using integers, fractions, or radicals. So that last sentence there already tells me that more than likely we should expect to have to use some of those structures, which means some of the numbers in this problem may not be quite ideal. That's one of the reasons I wanted to do this example. So first off, how do we know that this equation represents a hyperbola? We're looking for two specific things. So notice both x and y are squared, and then also notice that one of the terms is positive and one of the terms is negative. The fact that one of the terms is negative is what tells us this is a hyperbola. If both terms had been positive, then this equation would represent an ellipse instead. So we know that one of our terms is negative, therefore we know we are looking at a hyperbola. So hyperbolas have very interesting looking graphs. There are a lot of attributes that go into graphing this kind of equation accurately. We're going to focus on finding those and then translating them into a graph. So as always, we want to make sure that we're graphing as much as we can on paper, identifying all these attributes on paper first before we translate this into our homework system. And not only does this give us the practice that we need, but it also gives us a way to go back and check our work if we make a mistake. If we don't have things written down, then it's difficult to know where we may have made a mistake. So here's our equation. Let's get started. So first thing we want to determine is what the orientation of this graph is going to be. We have two possible orientations for a hyperbola. We can have a vertical hyperbola where the branches are stacked on top and bottom, and then we can have a horizontal hyperbola where the branches are stacked left to right. The way we determine which case we fall under is based on which of our two variables has a positive sign and which has a negative sign associated with its term. So in this case, our y term is positive and our x term is negative. Because the y term is positive, that tells us we have a vertical hyperbola. So we're going to have the branches of this hyperbola stacked vertically. So the orientation for our hyperbola is going to be vertical. So we're going to keep that in mind as we identify these attributes in order to make sure that all of our numbers are adding up and our graph makes sense. Now the next thing we want to find are our values for A, B, and C. Now remember, these are related to the denominators for these two terms, for our squared x and y terms. Now notice y squared does not have a denominator right now. If we want to give it a denominator, we can give it a denominator of 1. So that'll be the denominator we use in this case. Now, when we're graphing an ellipse, A and B differ by size. So A is always related to our larger denominator, B is always related to our smaller denominator. We find them in a different way when it comes to a hyperbola. So when we're looking at a hyperbolic equation, we're not focusing on which denominator is larger, we're focusing on which denominator is associated with our positive term. So y squared is the term that is positive, therefore the a is going to be associated with the y squared term. So a squared is our denominator, therefore a is going to be the square root of 1, which is 1, so our principal square root. B will be associated with whichever denominator goes with the negative term. So b squared is 20, which means b is going to be the square root of 20. And we want to simplify that. Now 20 is not a perfect square, but 20 is divisible by 4, which is a perfect square. So we can split that 20 up into a 4 and 5. We can simplify the square root of 4, which is 2, and just leave the square root of 5. So when we use the value b, we're going to use the number 2 root 5, not the number square root of 20. Okay, and then finally our C. C is going to be related to our foci. C is not something we directly see here, but C is going to be related to our a squared and our b squared. So for a hyperbola, C is defined as the square root of a squared plus b squared. So if we plug in a squared, we're plugging in 1, plug in b squared, which is 20. So we're adding those, we're taking the square root, so that's going to be the square root of 21. Now 21 is also not a perfect square, but the only numbers that divide evenly into 21 are 1, 3, 7, and 21. None of those numbers are perfect squares. So that's an indication that the square root of 21 can't be simplified any further. So when we want to reference the value for C, we're going to use square root of 21 as is. Okay, now that we have all these values, we're ready to proceed. So we'll start with the center. The center is not actually going to be on the graph of the hyperbola, but it's going to be our starting point, and it's going to be an important point of reference for our graph. So it's always going to be something of the form h comma k. H is going to be whatever number is subtracted from our x. So in this case, x minus 3. The subtraction is part of the standard form for the equation. So the number we're subtracting is going to be the x-coordinate of the center. So our x-coordinate for our center is going to be 3. Now the y-coordinate will be whatever number is subtracted from y. Notice in this case, y doesn't have a number subtracted from it. So it's implied that this number is 0. So the center of our graph, the starting point for all the other points that we want to graph, is going to be the point 3, 0. So I'm going to go ahead and add that to our graph. So our center is at 3, 0. And notice I've graphed it really small because, again, it's not actually a point that's on the graph. Think of it as a point of reference for finding the points that are going to be on the graph. So it's going to be our starting point. Now let's find our vertices. Since we're talking about a vertical hyperbola, the vertices are going to be above and below our center. So think of holding the x value constant. If we were to visualize this, we're holding the x value constant, and then we're distributing the vertices above and below that. So we're changing the y value while leaving the x value for the center constant. So our vertices, same x value as the center, start with the current y value, and then we are going to add and subtract whatever our value for a is. So 0 plus or minus 1. And if we split that up into two separate ordered pairs, that's going to be 3, 1 and 3, negative 1. So unlike the center, these 2 points will be points that are actually on the graph, that do actually make up the graph. Think of them as the starting points for each of the 2 branches of our hyperbola. So let's add those to the graph. So we have a vertex at 3, 1 and at 3, negative 1. And notice I drew those a little bit larger because, again, those are actual points on the graph that we want to show are included on the graph. Okay. The next things we want to find are the foci. Now, like the center, the foci are not actually on the graph, they're points of reference for the graph. That's where our C is going to come into play. So for our C, we are going to distribute our foci vertically. Now, with an ellipse, the foci fall short of where the vertices are. With a hyperbola, the foci are going to be further away than where the vertices are. So when we draw the branches of the hyperbola, the foci will be nested inside of the 2 branches. So we find them essentially the way we found the vertices. We're starting with the center and the distributing above and below by the amount square root of 21. So starting at 3, 0, we're going to add on and subtract the square root of 21. And if we split that into 2 separate points, that's going to be 3 times the square root of 21 and 3, I think I said times, 3 comma, excuse me, and then 3 negative root 21. There we go. And if we want to graph those, we can. Again, otherwise, those are just points of reference. So root 21, if we wanted to graph that, keep in mind we would need to approximate that. So particularly when we're graphing by hand, we could approximate that, get a reasonable estimate of what it is, and that would tell us where to graph. But otherwise, we don't absolutely need those since, again, they are just points of reference. Now, the next important attributes that are specific to a hyperbola are the hyperbola's asymptotes. Think of them as essentially guiding the shape. They're going to tell us how the edges of those 2 branches are bounded. So the general form for our asymptotes are going to be y minus k is equal to positive or negative, either a over b or b over a. That's going to be our slope. Now, which one we determine is based on which one of our 2 values was associated with y, what was associated with x. So notice in this case, a was associated with y and b was associated with x. So when we write our slope, we think of it as change in y over change in x. So a was associated with y, b was associated with x. So whatever a over b is, that's going to be our slope. And then in parentheses, we'll have x minus h. So I like to write this formula because it's a little bit more complicated than the formulas that we use for the vertices and for the foci. So I want to write my formula down and then I'll start plugging in numbers. Now k is going to be the y coordinate of the center and it's 0. So when we plug that in, it's just going to be y minus 0, which is just y. Now on the other side, we have positive and negative a over b. So a is going to be 1, b is going to be 2 root 5. Now, this is kind of an unfortunate looking number, but it's okay. That is your slope. That's an accurate value for your slope, so don't be alarmed if you see something like that. And then x minus h, essentially we're just copying what we see right here in parentheses, x minus 3. And there we go. And we want to write these in a better form. Keep in mind that this actually represents two separate lines. One version of this line has a positive slope and one version has a negative slope. So we're then going to go one step further and we're going to split this up into two separate equations. So our first equation, we have a slope of 1 divided by 2 root 5, and then that's multiplied by x minus 3. And then for the other, we have a slope of negative 1 divided by 2 root 5. And then that's multiplied by x minus 3. Okay, now if we want this in slope-intercept form, we know we need to go ahead and distribute our slope. Now we can do that to begin with, or another thing we may want to go ahead and start with is we may want to start by rationalizing our slope. By the very end, we're going to give a rationalized version, so it's ideal that maybe we go ahead and rationalize now. So if I want to rationalize this particular value, get that square root out of the denominator, remember I would multiply top and bottom by the square root of 5. If I simplify all of that, that's going to become the square root of 5 divided by the 2 that was already there times the 5 that was rationalized, which would become a 10. And then that would be multiplied by x minus 3. Okay, and then over here, same kind of thing, only difference is now it's negative. So negative root 5 divided by 10 times x minus 3. So these equations look almost the same with the exception that we have a positive slope versus a negative slope. Now I can find my slope-intercept form in one more step. I'm going to distribute my slope to these two terms. So that's going to be root 5 over 10 times x, and then root 5 over 10 times negative 3, think of the 3 as going with the numerator, so minus 3 root 5 over 10. And that does not reduce, so we're done. That's one of our asymptotes. Now, same thing over here. I'm going to distribute, and all that's really going to change are my signs. So I'm going to distribute this negative slope, so negative root 5 over 10 times x, and then these two negatives will multiply together to give a positive, so positive 3 root 5 over 10. Okay, now again, those are not very pretty numbers, but that's one of the reasons I chose this example. Even though the numbers feel difficult, the strategy we use in any situation is going to be the same. So when the numbers are easy, we use a strategy. When the numbers are more difficult like this, we use the same strategy, and we just fall back on those algebra skills. Now, as you can probably determine, graphing lines like this is going to be very complicated, but there is a shortcut. There's a way around it, and we're going to talk about that. We're going to talk about how you do that. Okay, so as we start to add additional things to our graph, notice we don't really have anything to help us right now. All we have is 2 points and the knowledge that the branches for this hyperbola are going to be stacked vertically, top and bottom. That is definitely not enough to get an accurate graph. So the method we use to get the most accurate graph is what's called the box method. We're going to draw a box that's sort of a reference, a point of reference, to help us accurately graph these asymptotes. Once we have the asymptotes graphed, then all we have to do is essentially connect the corners of our box representing those asymptotes, and then draw branches for our hyperbola following those asymptotes. But the focus here is getting those asymptotes graphed accurately, which again is a non-negligible kind of thing in this situation. Okay, so the box that we're going to draw is going to pass through these 2 points around the center. So the center of the hyperbola is also going to be the center of this box, and one dimension for the box is going to be that what we call the transverse axis that goes from one vertex to the next. Now, in order to draw a box, we have to have two dimensions. So we have a vertical dimension, we need a horizontal dimension as well. The horizontal dimension is going to be related to this value b. So notice we haven't really used b yet, with the exception of the denominator when we found our slope for our asymptote. Here's another example of where we're going to use b. So notice our vertices each are 1 unit above and 1 unit below the center. That's because a was 1. If we go in the other direction to get the other dimension of our box, that other dimension is going to be 2 root 5 times 2. So in other words, in each direction, we have to travel 2 root 5 units, whatever that looks like. But the trick then is figuring out where the corners of this box are going to fall. When we move that far, where are we going to be? Okay, so I wanted to work through this one so we can deal with this particular issue. How do we find the corners of the box if we need to accurately graph this asymptote? Where are these box corners going to fall? Because this is going to be really important when we translate this graph back into our homework system. So here's how we're going to find the box corners. We're going to start with our center. Think of that as the starting point for everything. So I'm going to write down the coordinates for the center. I'm going to leave some space after each coordinate. Okay, and then I want to think about what's going to happen as I translate from my center to the corners of this particular box. So what am I doing? How far am I traveling horizontally? How far am I traveling vertically? Okay, so each corner of the box is either going to be up at +1 or down at -1. So the y coordinates for the box are going to be at +1 or at -1. That means to get all the possible y coordinates for our corners, we're going to have to add and subtract 1, which was our value for A. Now horizontally, to get to a corner, we have to move b units. So traveling horizontally, we're going to move b units, which is going to be 2 root 5. We'll move 2 root 5 in the positive direction. We'll move 2 root 5 in the negative direction. So our corners are going to be 3 plus or minus 2 root 5. So again, this is our A, this is our B. Now, we need to come up with all 4 pairings. What I mean by that is plus and plus, plus and minus, minus plus, minus minus. This formula right here actually represents 4 different ordered pairs. So we want to write out all 4 of those ordered pairs because those are going to be the ordered pairs that represent the corners of this box. So our first x coordinate, 3 plus 2 root 5. And keep in mind, you're going to write it like that, you're going to type it like that. There's no way to simplify that above and beyond just approximating, which we want to avoid doing, particularly as we translate this into our homework system. Okay, and then we'll also have 3 plus 2 root 5 and 0 minus 1, so -1. Okay, now we need to look at the possibilities where we have 3 minus 2 root 5. So 3 minus 2 root 5, +1, and then 3 minus 2 root 5 and -1. So those are going to be the corners of our box. Okay, so again, we know things are going to be up at 1, down at -1, and then distributed horizontally. So if we could get a good approximation for whatever this number is, then we would know where our horizontal distances or displacements are. So this is going to be one coordinate on x, this is going to be another x coordinate. Okay, now clearly our hand-drawn graph is not going to be super accurate because it is going to require some approximation. So one thing you may want to do, if you've got a calculator, go out to the side for just a moment and then see if you can figure out what 3 plus 2 root 5 is. So 3 plus 2 times the square root of 5. So let's check that. I'm checking it in my calculator as well. So 2 times the square root of 5. Okay, that's about 4.47. And then we are adding 3 onto that. And that gives you about 7.5. So that first x coordinate is about 7.5. Okay, so that means one of our box corners is at about 7.5 and 1. So let's see if we can sketch that. So here's 5, 6, 7, 7.5 and 1. Okay, so that would be right there. Again, I'm drawing it small because it's not really there. It's a point of reference. That means the other box corner would be at about 7.5 and negative 1. So that would be right here. Okay, now 3 minus 2 root 5. So multiply 2 times the square root of 5. Okay, and that's negative. And then we have an additional 3. And that's going to be about negative 1.5. Okay, so x is negative 1, negative 1.5, and then up to 1, down to negative 1. Okay, so even though this is an approximation, we can make sure that these numbers make sense. As with all the attributes for all of our graphs, everything is always distributed evenly. So vertically speaking, things are distributed evenly. And then notice if we go left to right, the corners of the box appear to be equally distributed from vertex to each corner. So these numbers, this positioning makes sense. Now, these are the corners of a box, so I'm going to connect them. Now, I'm going to connect them with a dotted line, and the reason I do that is because, again, these points are not really there. They're points of reference to help me accurately graph this hyperbola, more specifically graph its asymptotes. So I'm connecting the corners of my box like this, drawing the box. And then how do we use the box? So we've got the box. That was the hard part. The way we use this is by then taking a ruler, a straight edge, something like that, and you want to connect the opposite corners of your box to form your asymptotes. Just like with the box, I'm graphing this using dotted lines. Asymptotes are imaginary boundaries. They're not really there. They represent the absence of points. So when I graph them, I'm graphing them to use as reference. But in order to indicate that they're not really there, that they really represent the absence of graph, the absence of points, I'm graphing them as dotted lines. And there we go. So the benefit of using this box method is we don't have to go through the steps to graph a line that has a slope like this and a y-intercept like this. Graphing that accurately would be very hard. Here, we've got a graph that's much more accurate. So our hyperbola is going to pass through each vertex, and then it's just going to follow the shape formed by our asymptotes. And it's not going to be perfect, particularly when you're doing it by hand. But if you have all those numbers to back it up, then you've got pretty much the degree of accuracy you need. So the actual hyperbola is what's graphed solid, again passing through those two vertices. So there was a lot of work involved here in getting all of these attributes and getting that graph. Now let's translate it into our homework system. So let's switch gears, and put this in the homework system. So we're going to go through and type in all the attributes first, and then we'll see if we can translate things onto our graph. Again, I wanted to do this problem in particular because I want to show you what's going to happen when you have these numbers that aren't quite ideal. So let's start with the center. So our center was pretty simple. So it was 3, 0. Let's confirm that. Okay, that looks good. Okay, now our vertices, we had, again, pretty easy points. So 3, 1, and then 3, negative 1. Let's check those. Okay, those are good as well. Now, the foci, that's where it gets a little bit more complicated to type. And again, we were warned at the beginning, integers, fractions, or radicals. So radicals are realistic in this case. Fortunately, it's built in for us to be able to type them, so we don't have to worry too much about that. So our first focus is at 3 root 21. So I'm going to use my square root tool, root 21, and then 3 and negative square root of 21. Okay, let's check those. Okay, those are right as well. So if you were worried about the numbers up to that point, that's confirmation that we're on the right track. And then we've got our asymptotes. Notice we're looking for slope-intercept form where y is isolated, and we have that. So let's type each of those in. That's going to be the most work for typing. So we need fractions and we need radicals. So for our first asymptote, its slope was the square root of 5 divided by 10. That is, of course, multiplied by x. And then we had a y-intercept at negative 3 root 5 over 10. So minus 3 times the square root of 5 divided by 10. Okay, and the next one is going to look virtually identical, except the signs are going to flip. So we'll have a slope of negative root 5 over 10. That, of course, is multiplied by x. And then we are adding 3 root 5 over 10. So 3 square root of 5 divided by 10. Oops, let me fix that. 3 square root of 5 divided by 10. Okay, and double check it. That was a lot of work to type, so double check that that was exactly what you wrote down. Make sure that's exactly what you want, and then you can check it. Okay, so that's good news. That was the hard part. Getting up to that point was the hard part. Now we're just going to translate what we have on our written graph onto our homework system. Okay, so let's look at the scale first. It looks like our x and y, we're counting by 1, so that's good. It's going to be easy to drag and drop points as much as possible. Okay, now also we have the hyperbola tool built in, and it's going to look for some specific things. So let's go ahead and click the tool and let's see what it wants. Now number 1, we're going to need the center. We know our center is at 3, 0, so I'm going to go ahead and place that. Okay, now we need to place a vertex. We have a vertex at 3, 1, so we can go ahead and place that. Now we need to place the asymptote. This is where it gets complicated. Okay, so in order to accurately place an asymptote, we need to know where the corners of the box are. Now, best case, easy numbers, you just drag and drop the box corners and you don't have any problems. In our case, remember our box corners didn't fall at integer values. So this is where we're going to go, and we're going to use the point plotter. We're going to type in the coordinates of one of the box corners, and it's not going to matter which one you use, just pick one. So the first one we had was 3 plus 2 times the square root of 5. That was our x coordinate. And then the y coordinate was 1. Excuse me, let me go over to the y coordinate. Y coordinate is 1. And notice it draws a little x on the grid for you. So you're going to plot that point. Okay, let's see if that's enough. Now it's cleared out what we graphed so far, so let's go back into the hyperbola tool, use it again, and let's see if that gives us enough. So we need to place our center at 3, 0, so here's 3, 0. Place our vertex at 3, 1. And then notice now we have that little x. We can snap to that location when we're placing our asymptote. And what's nice is we only have to place that one corner. It knows how the other corners are going to be evenly distributed based on where that one corner is. So as a reminder, how did we do that? How did we accurately place that corner? We went into the plot a point tool and we plotted one of those corners by typing in coordinates. So we used 3 plus 2 root 5 and then 1. You could have used any of those corner coordinates that you want, and then your asymptote tool will snap to that location. Okay, so cross your fingers, hope for the best, check your answer. Perfect. Okay, so that's good. Now this one was a hard one. Not everyone you graph is going to be this involved. It gets involved when we have these numbers that aren't perfect squares. 20 wasn't a perfect square, which is what initially created the problem with these kind of numbers. But it's doable. You just have to take your time. You need to fall back on what you know about these graph attributes. And again, make sure you do as much on paper as you can before you try to put it into your homework system. So what if you plot this and it doesn't end up correct? More than likely the mistake is with your asymptotes. I would say 9 times out of 10 the mistake is with your asymptotes. If your asymptotes fall on non-integer values, you're not going to be able to use the grid that's built in. If you can't just drag and drop using the grid that's built in, you're going to have to plot points by typing coordinates in order to get things accurately. Remember, this particular system does not allow for approximation. So anything you do that doesn't use exact values, that involves approximation, is going to result in graphs that are inaccurate. So if your graph is marked incorrectly, go back and check your vertices, check your center, check all those attributes. They should be good up to that point, but most importantly, check the corners for the box and for the resulting asymptotes. So that is graphing a hyperbola in the Connect and ALEKS system.